It's kind of wild to think, isn't it? Just a short while ago, you had quantum computing over here and AI, well, way over there.
Absolutely. Different conference halls, different problems,
Yeah.
completely separate tracks, really.
But something's definitely shifted.
It really has. We're seeing this convergence, a really exciting one, between these two, frankly, incredibly powerful fields.
And that's what we're digging into today, right? This intersection.
Exactly. Quantum computing and artificial intelligence. You've got an article that dives deep into this, and our mission, if you will, is to pull out the key stuff, why it matters, why there's all this buzz.
Yeah, because you might be sitting there thinking, okay, fine, but why bother? We've got supercomputers that are already, mind-blowingly fast.
That's a fair question.
And AI models crunching insane amounts of data. What's the big deal about adding quantum?
The thing is, and the source really nails this, some problems just explode in difficulty for classical computers. They scale exponentially.
Right, add a little complexity and the computing time goes through the roof.
Precisely.
Hmm.
But for quantum computers, those same types of problems, they seem to scale much more, let's say, politely, more manageably.
Okay, so quantum handles certain types of scaling better.
Yes. And that's where the AI comes in. It's the intelligence layer. Think about it like AI is great at pattern recognition, learning, making smart choices based on data.
Right.
Quantum computing offers this fundamentally new engine for certain calculations. The source uses this analogy I quite like. AI is the skilled pilot, knows the destination, knows how to navigate complex situations.
Okay.
And quantum computing, that's the powerful jet engine. It gives you the raw thrust to tackle things you just couldn't before.
I see. Pilot needs the engine needs the pilot.
Exactly. Put them together,
Okay.
and, well, you can go places you couldn't even dream of otherwise.
Nice. That makes sense. Our source also gives us a bit of a heads up on terminology, which is helpful.
Yeah, just a quick shorthand.
When we're talking about the general collaboration, we'll say quantum computing and AI.
Right. Broad strokes.
But if the AI is specifically like directing the quantum hardware, telling it what to calculate.
Then it's AI and quantum computing, software guiding hardware. Hopefully that helps keep things clear as we go.
Yeah, should do. Okay, so who are the main players making this happen? Where's the action?
Good question. The article gives a really nice tour of the key labs. Let's start with Google Quantum AI.
All right, down in Santa Barbara. I thought the detail about naming their fridges after Pokemon was kind of fun.
Huh. Yeah, adds a bit of personality, doesn't it?
Yeah.
But seriously, they made waves with Sycamore, that whole quantum supremacy thing.
Yeah, showing their chip could do a specific, very particular calculation faster than a top supercomputer. A narrow task, but still.
It was a milestone.
Mm-hmm.
But their bigger game now seems to be marrying those quantum chips with their big AI models. Think Gemini.
So the AI could potentially offload the really tricky computational bits to the quantum processor.
That's the vision, yeah.
Hmm.
And AI is smart enough to know when and how to use the quantum advantage. And they've got TensorFlow Quantum too.
Ah, right. What's that for?
It's like a sandbox, a place for researchers to start playing with hybrid algorithms, combining classical and quantum steps without needing, a PhD in quantum physics to get started, lowers the barrier to entry.
Okay, interesting. Then there's NASA, their QuaIL lab.
Yep. Quantum Artificial Intelligence Lab at Ames. Their focus is very applied. Things like optimizing spacecraft paths.
Oh, wow.
Designing better antennas, figuring out the best schedules for Mars rovers, stuff where even small improvements save huge amounts of money or enable new missions.
Makes sense for NASA. And they took a slightly different hardware route initially.
They did. They were early adopters of D-Wave's quantum annealers. Those were machines built specifically for optimization problems.
Right, not general-purpose quantum computers.
Exactly. And what they found, which is really interesting, is that even that early, somewhat noisy hardware, when you paired it with reinforcement learning, a type of AI, it could actually beat some standard classical methods on certain optimization tasks. It shows you don't necessarily need a perfect quantum computer for it to be useful if you guide it smartly with AI.
Brains and brawn, sort of.
Kind of, yeah. And then, of course, there's IBM Quantum. Big presence.
They seem steady, like a long-term play.
I think that's fair. They open-sourced Qiskit, their software platform, which was a big deal for building a community.
Right, get more people using their tools.
And they've been consistently upping their Qubit counts over 400 now. They're also really pushing quantum kernel methods.
Okay, what are those, roughly?
Think of them as ways to use quantum mechanics to help machine learning find trickier patterns in data. patterns that classical algorithms might miss.
Gotcha. And they have a roadmap, right, towards more stable qubits.
Yeah, aiming for over 1,000 logical qubits with error correction built in by around 2030. Their view is very much about quantum and AI evolving side by side, each helping the other along.
It's not just the giants, though, is it? The article mentioned a wider field.
Oh, absolutely. It's crowded. You've got Microsoft with Azure Quantum looking into topological qubits, theoretically more stable. Amazon's in the game with Bracket, their cloud service. They're even helping banks explore quantum finance applications.
Thanks. Interesting.
And then a whole ecosystem of startups, Rigetti, IonQ, Xanadu, each with their own unique hardware approach. Plus, tons of university research. It's a real mix of collaboration and competition.
Sounds dynamic. And all this activity is leading to new ideas like this quantum CAE thing.
Ah, yes. Tadashi Katawaki's concept. He calls it CAD for hypotheses. Computer-aided engineering, but for scientific ideas.
Okay, CAD for hypotheses. Unpack that a bit.
The basic loop is AI proposes something, a molecule, a circuit design, whatever.
Right.
Then a quantum simulator, or eventually a real quantum computer, tests that proposal rigorously.
Runs the numbers, basically.
Yeah, exactly. Machine learning then looks at those results, digests them, learns from them, and feeds that back to the AI to propose the next idea. It's an autonomous loop of propose, test, learn, repeat.
Wow. Putting discovery on autopilot.
That's the vision. Katawaki even maps it to levels, like self-driving cars.
Oh, okay. How does that work?
Level 1 is just basic automation, scripting tasks. Level 2, maybe robots doing experiments, but humans are watching closely.
Standard lab automation, maybe?
Sort of.
Mm.
Level 3 is where it gets interesting. Conditional autonomy. The AI runs whole experiments itself, but under very specific predefined conditions. Level 4, high autonomy, the AI starts adapting. If it gets weird results, it might change its own experiment, maybe even ask new questions.
Okay, that's getting sci-fi. And level 5?
Full autonomy. Humans set a broad goal, like find a better battery material, and the AI just goes off and explores, figures out the path itself.
Whoa, but the article says we're seeing bits of level 3 already.
We are, yeah. Think AlphaFold predicting protein structures.
Yeah.
That's kind of level 3 for biology.
Right, that was huge.
Or D-Wave optimizing circuit board layouts with their annealers. That's level 3 in design. But getting to level 4 and 5, that needs much more powerful, much more reliable quantum computers to really work. The AI can generate ideas faster than current quantum systems can test them, often.
Okay, so the hardware needs to catch up to the full vision, but where are we seeing real-world ripples now? Where is this quantum AI combo actually starting to make a difference?
Drug discovery is a huge one. The sheer number of possible molecules in the chemical universe is just astronomical.
Too big to search manually or even with classical simulations alone.
Exactly. But quantum algorithms, like quantum phase estimation, could potentially calculate exactly how well a drug molecule binds to its target protein. That's a key property.
So quantum does the precise calculation.
And AI models, trained on existing chemical data, can intelligently filter that vast universe, pointing the quantum computer towards the most promising candidates first. It massively speeds things up.
And big pharma is noticing. Pfizer, Roche.
Well, yeah. The article mentions they have internal teams with quantum computing AI, literally in the name. That tells you something about the perceived potential.
Definitely. What about material science? Finding new stuff.
Similar idea, huge potential. Imagine finding room temperature superconductors. That would change everything.
Game changer.
The approach is AI learns from known materials, suggests new structures. Quantum computers then calculate key properties, like electronic band gaps, crucial for conductivity.
So AI suggests, quantum verifies.
Or scores the suggestions, yeah. It makes the discovery process much less trial and error. There was this anecdote about AI suggesting designs for perovskites.
Okay.
And the ones that got high scores from quantum-assisted checks were twice as likely to actually work when they made them in the lab compared to traditional designs.
Wow, that's a concrete result. Twice the hit rate.
Yeah. Then you've got optimization and logistics. This feels maybe more near-term.
Like the Volkswagen traffic light trial.
Exactly, in Beijing. Using D-Wave annealers again, plus reinforcement learning AI to manage traffic signals.
And it worked.
They reported cutting wait times by up to 15% in peak hours. The AI was crucial for translating the messy real-world traffic problem into something the quantum annealer could chew on, and then using the results effectively. It's that brains plus brawn thing again.
Real benefits for people stuck in traffic. What about finance? That seems like another area ripe for optimization, but also risk.
Both, definitely. On the risk side, everyone knows powerful quantum computers could break current encryption, like RSA.
Yeah, the security underpinning, online banking, everything.
So banks are heavily investing in post-quantum cryptography, new encryption methods that are quantum resistant. That's defense.
Makes sense.
But they're also exploring the offense, if you like, using quantum, guided by AI, to improve their own financial models. Things like portfolio risk assessment.
How would that work?
Well, the article mentions running a complex risk calculation, Monte Carlo value at risk, on Xanadu's photonic chip.
Mm.
But an AI, an LSTM network, was used to predict market volatility to feed into that quantum calculation.
Ah, so the AI provides context or parameters for the quantum part.
Exactly. The speed up might be small today, but they're building the tools and techniques for when the hardware gets better.
Laying the groundwork. And finally, climate science. That sounds incredibly complex.
Hugely complex. Climate models are massive, tons of interacting physics. Quantum solvers might, eventually, help tackle the really hard math, the partial differential equations, at much finer detail.
Or simulations.
Potentially, yeah. And AI can help too by filling in gaps in observational data, maybe from satellites, or by creating faster emulator models. The combination could mean better predictions for things like storm tracks or intensity. High stakes there.
Absolutely. The article then shares this interesting little experiment, almost a personal story, about classifying data.
Ah, the Swiss roll dataset. Yeah, it's a classic machine learning challenge. Its data shaped like a, well, Swiss roll curled up and nonlinear.
Hard to separate the layers cleanly.
Very hard for standard algorithms like a support vector machine, which the author tried first. It basically failed. But then they used a quantum kernel method. Remember those things IBM's working on? Running on a 27-qubit machine accessed through the cloud. Near perfect classification, just like that.
Wow.
And the reaction was immediate. People replicating it within hours, VCs apparently calling. Just shows how quickly a promising result, even a small one, can ripple through this field right now.
It really highlights the excitement. But okay, let's be realistic. It can't all be smooth sailing. The article mentions speed bumps, right?
Definitely. And it's crucial to talk about them. The biggest one is still qubit quality. Decoherence.
Meaning the qubits lose their quantumness too quickly. They're fragile.
Extremely fragile. Error rates are still much higher than in classical computers. Improving that and then scaling up systems with good qubits is proving really, really hard. Much harder than scaling silicon chips or even big AI models.
Right. It's not just about adding more qubits if they're all noisy.
Exactly. And then there's the interface issue. If your AI model is trying to learn from the output of a noisy quantum computer, well, garbage in, garbage out.
The AI can get confused by the quantum errors.
It can, yeah. It's really a challenge.
But people are working on fixes, presumably.
Oh, absolutely. Lots of smart people. They're developing software layers for error mitigation, trying to estimate and subtract the noise, using clever statistical methods like Bayesian techniques after the quantum computation to clean up the results,
Okay.
and designing hybrid algorithms where you only give the really hard quantum part to the quantum computer and do the rest classically to minimize the impact of noise. It's a constant battle, lots of ongoing R&D. Progress is happening, but it's tough work.
This whole picture seems to be leading towards a fundamental change in how science gets done. Michio Kaku's quote about turning discovery into an industrial process. That's a big statement.
It is a profound idea. And
Yeah.
you see hints of it in projects like the AI Scientist.
What's that?
It's an AI system that can read scientific papers, literally ingest them, form its own hypotheses based on that reading.
Seriously.
Yeah, and then write code to test those hypotheses on quantum simulators, and even draft initial papers about the results.
That's incredible. Does it work?
Well, humans are still checking everything, obviously, but the article notes a surprisingly high percentage of its chemical predictions are actually being confirmed when tested in a real lab. It's promising.
Combine that with Katawaki's quantum CAE loop.
And you can start to see that conveyor belt for discovery taking shape. AI and quantum working together, iterating rapidly.
It does raise weird questions, though. Like, who gets the Nobel Prize if the AI makes the discovery? Lines of code.
Exactly. And you see venture capital pouring money into startups, building fully automated lab pipelines. It's not just theory anymore. People are betting real money on this automated future for science.
The definition of scientist might be changing.
It really might. The role of the human researcher is definitely evolving.
The article then circles back to Google, mentioning a shift in their focus, less about just showing off speed, more about reliability.
Yes, exactly. That initial Sycamore Supremacy demo was important. But they know for quantum computers to be useful, Especially for complex AI tasks, they need to be reliable. Error correction is key.
Right, dealing with that noise problem we talked about.
They did a recent demo with an 8-qubit tile using something called the surface code. They showed that as they made the code bigger, the logical error rate actually went down.
Okay, what does that mean in simple terms?
It's like learning to ride a bike without training wheels. It's proof the basic principle of quantum error correction works. A massive step towards building fault-tolerant machines that can run long, complex calculations.
A foundational step. And they might offer this as a service. Quib engine.
That seems to be the idea, making robust quantum compute power accessible via the cloud, much like they do with AI models today.
And the other part of their strategy? Using LLMs like Gemini as quantum orchestrators.
Yeah, this is really fascinating. The vision is an AI that can understand a scientist's goals, maybe from reading their lab notes.
Okay.
Figure out what calculations are needed, translate that into instructions for the quantum computer, schedule the job on the hardware, get the results back, and then summarize them for the scientist in plain English.
Wow, so the LLM acts as the ultimate intelligent interface to the quantum hardware.
Pretty much. A seamless bridge between human intention and quantum execution. That would be incredibly powerful.
And Google has an advantage here because of their software tools like Cirq and TensorFlow Quantum.
That's a huge strategic point the article makes. By open sourcing these tools and providing data sets, they make it easy for new researchers to learn and build within the Google ecosystem.
So new talent defaults to their stack.
It creates this network effect, yeah. Similar to how NVIDIA's QD became dominant for GPU programming in AI, it could give them a real long-term edge in shaping how this whole field develops.
It feels like the way science itself is done is changing too, this idea of Centaur teams.
Right. Not the mythical half-horse, half-human,
No.
but human experts working with AI systems. The article gives a great example. A Centaur day, trying to design a better battery.
How does that play out?
The human scientist sets the direction we need higher energy density, better cycle life, using their deep chemistry knowledge.
Okay.
The AI, trained on mountains of battery papers and simulation data, suggests specific chemical tweaks or structural changes.
Generates ideas.
Then the system runs quantum simulations of those ideas, maybe on cloud hardware. Machine learning analyzes the simulation results, looking for promising signs.
Right.
And the human scientist looks at those results, uses their intuition. This looks promising, but what about stability? And guides the AI on the next round of suggestions. It's this iterative loop.
Humans steer, machines churn through the possibilities.
Exactly. A collaborative workflow leveraging the strengths of both.
But looping back to the challenges, the article ends by reminding us it's not all solved yet.
Noise?
Data bottlenecks.
Yeah, it's important to keep our feet on the ground. Qubit noise is still the big one. Getting data in and out of quantum computers efficiently is another major hurdle.
The I/O problem.
Right. And sometimes, even when these quantum AI models work, we don't fully understand why they work. The interpretability issue.
The black box problem, but maybe even weirder with quantum.
Potentially, yeah. So, lots of progress, but still significant engineering and scientific mountains to climb.
Okay, so if we had to boil it all down, what's the main thing you think listeners should take away from this deep dive today?
I think the biggest thing is this really powerful synergy that's emerging. Quantum computing and AI aren't just interesting fields on their own anymore. Their combination is starting to look like something genuinely new and transformative.
More than the sum of its parts.
Definitely. We're moving past pure hype now. We're seeing the beginnings of real applications in medicine, materials, finance, logistics. This convergence really could reshape how we discover things, how we engineer solutions.
It does feel like we're right at the start of something potentially massive, and I liked the final thought in the article's epilogue. It's not just for spectators.
No, exactly. It's a call to action almost. The future here belongs to the people who are willing to jump in now. The builders, the experimenters.
People willing to learn the basics, maybe try building a small quantum circuit, collaborate across disciplines.
Precisely. Learn some linear algebra, play with Qiskit or Cirq, talk to scientists in other fields about their hard problems. It's about getting involved. Because, as you said, we're just scratching the surface of what this combination might unlock. The real breakthroughs are likely still ahead.